Welcome to our webinar series, Modernizing Your Geospatial Reference Systems, organized by the United Nations Global Geodetic Center of Excellence. Today, we look into part 4 and introduce you to the height datum. Before we start, I would like to introduce myself. My name is Jan Dostal and I am seconded from German Federal Agency for Cartography and Geodesy to the UN-GGCE as a technical advisor. For those of you who are already familiar with the previous parts of the webinar, this graphic must be already familiar. Today, we cover the fourth and last part of the seminar series concerning Geospatial Reference System, the height systems. The vertical datum is a part of Geospatial Reference Frame, like the time-dependent reference frame or static datum on the left. But the height component deserves special attention as there are some particularities that need to be considered. In this session, we will discuss especially questions covering the topics: what is special about the height component and where we need it. Before talking about the height system, we will discuss the shape of the Earth, the 0 point of height. Then we will have a look at the gravimetry measurement, show how the vertical datum can be realized, and at the end, we present some interesting global application for the height system. Let us start asking the question, where help us the knowledge of exact height? The height component help us to know which way flows the water, and with this information allows us to carry out the right flooding risk management. It helps us to know where to build channel between a river or how to create sewage systems in the cities or drainage and irrigation system in agriculture. It answers the question about the right inclination of railways or roads, or to ensure the secure deepness below a ship in shallow waters, but also to determine scientific questions like the quantification of the sea level change or other dynamic processes of the Earth with respect to height, as well as to describe the topography. What is the height of the top of the mountain or depth of the ocean? Traditionally, when we speak about the height, we mean the height above the sea. Therefore, the height component is a description relative to sea level, which built the zero surface. To account for the zero surface at the sea level, we can use either a physical shape of the Earth, which is defined by gravitational potential, or geometric shape of the Earth, the one satellite positioning system used for the height determination. Two different shapes of the Earth, but which one is the right one? This is the question we should look at. We listed just some of the purposes where the information about height has a relevance for our society. And now we can start to discuss the topic from technical point of view. Before talking about the height, we should ask the simple question, what is the shape of the Earth? Even if we know nowadays that the Earth is not a flat disk, there are different possibilities how we can represent the shape of the Earth. We have the mathematical approximations, like the sphere, which is a regular geometric body neglecting any irregularities and even the flattening on the poles, quite often used by analysis in geoscience as it considerably simplify the calculations. And then we have an ellipsoid, also geometric approximation, but considering the flattening of the Earth at the poles. The next shape we should take in account is the topographical surface of the Earth, a physical shape we experience on daily basis. But there is one additional physical representation of our Earth, the geoid, which follows the gravitational potential, and we look at this particular shape in more detail. Easily explained, the geoid is a form of the Earth that the Earth would take if it would be completely covered by water. As you know, the water, following the gravitational force, flows always downwards. Now imagine the Earth is covered just by ocean. There are no continents. Then the shape of the Earth would take the shape of a geoid, like shown in the picture. The water equilibrium will not give a perfect geometric body. There will be differences in height in respect to the geometry. The reason is that the water follows the gravity force, and the gravity depends on mass distribution. And as the interior of the Earth doesn't consist of homogeneous material, so is also the mass distribution inside the Earth not homogeneous. This is reflected by the varying values of gravity force at the surface of the Earth. The geoid is defined as a surface with a constant gravity potential at sea level height. Therefore, the geoid is a gravitation equipotential surface at sea level. The different colors in the picture emphasize the variations of the height following the equipotential surface. Be reminded that the real variation of the height are about plus minus 150 meters. To make them visible, the scale of the height in the picture is exaggerated. Introduced the different shapes of the Earth, we turn back the height system. It is one-dimension coordinate system used to define the distance of a point from a reference surface along a well-defined path. It is complex description as there are a number of reference surfaces and a number of well-defined paths. Following the different shapes of the Earth, there exist also two basic types of height systems: geometric, ignoring Earth's gravity field and using geometric straight line paths, like by GNSS, and physical, linked the Earth's gravity field and measured along the curved plumb line. Example criteria are the orthometric heights. To better understand what does it mean, we will explain it in more detail in the following slides. Drawing a profile of a piece of landscape, we start with the topographic shape, which is familiar for all of us, and where we display some terrain and sea. Now we turn to the geometric shape of the Earth, and we display in our drawing the ellipsoid in red. The ellipsoid is the geometric zero surface we measure the height from. Additionally, in purple, we display also the ellipsoid normal, which is the straight line along which we measure the geometric height. Therefore, the geometric height of the point P on the Earth surface is the height described with small h. You may also recognize on the right in the figure that the ellipsoid and the mean sea level are not on the same level. This is in general the way as the sea doesn't follow the geometric form. As already discussed, the physical shape of the Earth is described by geoid, which represent now the zero value for measuring the physical height. Here represented with the red dashed line, as well as the line along which the physical height is described. You may ask why this line is not geometrically straight. The reason is that this line shows the direction of the gravity force. It is the plumb line. When we display the geometric and physical height of the point P on the surface in one figure, we see a discrepancy between the two systems and may ask, what is the right to measure the height? The truth is, both are right. You just use different height systems. The difference between the two heights, the geometric and the physical one, we can call geoid height or geoid undulation and assign it usually with capital N. The difference between the two vertical lines of height is then the deflection of vertical. To make the differences between the two systems visible, the scale in the picture are exaggerated. In reality, in comparison to the size of the Earth, they are rather small. Now, as we learn the theory behind the height system, we can turn to the gravimetry. As already explained, the physical shape of the Earth, the geoid, is defined by a surface with equal geopotential. Therefore, to determine numerically the geoid, we need to measure the gravitation force of the Earth. On the slide, you see different gravimeter types for these purposes. Generally, in dependency on used technology, we divide between relative and absolute gravimeters, where the relative gravimeters can measure only the difference or change in the gravity value. The absolute gravimeters can determine the absolute value of the Earth gravity on the given spot. The relative gravimeters can be further divided in spring or superconducting gravimeters, where the absolute gravimeters measure gravity with help of a free fall of either a test mass in vacuum chamber or with help of quantum technology. In the previous slide, we had just a look at some examples of the terrestrial gravimeters, but this is just one of the possibilities to measure gravity, very exact, but only punctual gravity values. But we can also use airborne gravimetry, where there are gravimeters on board of airplane or helicopter, which allows to measure the gravity values along the flight tracks. The same applies for ship gravimetry, to obtain gravity values over areas covered by water. Another technology is the satellite gravimetry that allows to cover the whole Earth. The result from such permanent gravity satellite missions offer global coverage with gravity measurements every month, but with smaller resolution and accuracy than the terrestrial or airborne gravimetry. A global Earth geopotential model is then the result from the analysis and combination of the collected data from different gravity components and individual missions and campaigns. With this model, we obtained the numerical basis for the zero surface to measure the physical height. The figure displays one of such models, the Earth geopotential model from 2008. Now we can turn to the realization of the vertical datum. Discussing sufficiently the geoid, the physical shape of the Earth, can introduce the vertical datum, the reference surface for height and depth measurement. Vertical datum is defined by measuring the sea level at tide gauges over a period of time, and then holding the mean sea level fixed in an adjustment of the leveling network to transfer height from the tide gauges inland. The height reference system is then defined by the vertical datum and the type of height. But first, let us discuss how to transmit the physical height. How can we measure the physical height difference between two objects at different places? Important step is to establish a reference with the same height. In the second step, we can measure the height difference of any object in respect to these leveling reference. The easiest way to establish a leveling reference is the use of the water level device, where two glass vessels are connected with hose. Filled with water, this simple system established a physical level of the same height. The distances to this reference level allows us to determine the vertical distance between the objects at different places. For transmitting the height across a country with very precise accuracy, an optical or electronical level device together with two leveling graduated stuffs is used. Once the level device placed in the middle distance between the two graduated stuffs, we read the height values crossing the horizontal line on each of the stuffs. The metric height difference between the 2 points on the ground equates to the difference between the two numerical values on the stuffs. The principle explained on one step, we can now start transmit the height over long distances, lining up this setup from datum point A to datum point B. The height difference between the datum points or the points of interest is then the sum of the distances of the intermediate steps. The intermediate steps are temporal, used just for the height value transmission. Now we have a look at some example of the market points or datum points for the height. Quite often, the height mark is on a side of a stable pillar and generally round. The reason for that is the accuracy. A round mark as a reference has just one singular highest point and not a flat area that could be uneven. As already mentioned, a vertical datum is defined by measuring the sea level at tide gauges. On the photo left, you see the historical tide gauge from Kronstadt. In the figure on the right, then the principle of the tide gauge. By the tide gauge, the sea level movement is permanently monitored. From this vertical movement, a mean sea level can be calculated. At some time, the value for the mean sea level is fixed and marked as a zero height. This value is then transmitted via leveling to the vertical datum points distributed across the land. We explained all the essential elements for creating the vertical datum. And now we bring the elements together. In the picture on the right, you see the Australian leveling network. All the lines in the map mark the leveling tracks we already discussed. In the zoom, it is over 200,000 kilometers of leveling to transmit the height across the whole country. In addition to it, the black points on the coast mark the tide gauges. There are 30 of them. The 0 point for the vertical datum in Australia is given by the average value of these 30 tide gauges. In Europe, the situation is different than in Australia. Historically, every country created its own vertical datum and used for this purpose different tide gauges as a zero reference. The different colors mark the individual vertical reference system, and the numbers in the map mark then the differences between them. The countries that are bright green colored in the east of Europe use as a reference the tide gauge of Kronstadt we showed you already in a picture. As other examples, the tide gauges in Amsterdam, build a reference for Netherlands and Germany, Marseille for France, or Alicante for Spain. The different height systems across one continent create inconsistencies at countries' borders. So can a mountain peak that is placed exactly on country's border have two different heights and both will be right. Up to now, we were talking about a physical height system. Now we turn our attention to the geometric height, the one GNSS used to work in. The reference surface is the ellipsoid, in this figure in green. In black, there are also some of the continuous observing reference station drawn, so-called cores. The green arrows indicate the known height of these stations above the ellipsoid. Now we include the other part of the GNSS system, the space segment. Observing the flying satellites with help of the core stations, we can calculate the satellite orbits, the flying track of the satellites. Knowing the ellipsoidal height of the core stations, the relation between the GNSS satellites and the core station allows us to calculate the ellipsoidal height of the satellite orbits. With the satellite heights known, we can easily, with a common GNSS receiver, use the broadcasted satellite signals and estimate the ellipsoidal height at any place on the Earth. This geometric method seems to be for the user much easier than the laborious leveling. But the truth is that this geometrical method is also less accurate than the leveling and for many geodetic applications not sufficient. We illustrate in the figure just the estimation of the height component with GNSS. But the same principle applies also for the horizontal part and therefore for the 3D coordinate. As we already did in the theoretical part, we introduce the physical and the geometric shape of the Earth, we combine in this slide the two different height systems in practical sense. First, we measure the height of our GNSS antenna geometrically with GNSS, and we obtain the ellipsoidal height of the antenna, small h, in green. In the next step, we level from the sea and use additionally gravity values to obtain the proper orthometics height of the GNSS antenna above the geoid, assigned with capital H. With the discrepancy of the two measured values of height, we can estimate the geoid undulation, assigned with capital N in black. The respective basic relations is written on the left. In the last part of our agenda, we demonstrate some practical examples to show the importance of height component. In the following example, we look at safe shipping. Maybe not on the high sea, but in shallow waters along the coast or in areas like, for example, the Baltic Sea, where the water is shallow. To not run aground, it is of great importance to know exactly if there is enough space below the ship to the ground, the so-called underkeel clearance. For answering this question, one has to consider different aspects. We start with a figure where we display just some sea with its bottom. We add the reference surfaces we learned about, the ellipsoid and the geoid. Additionally, we assume we know already the bathymetry, the seabed topography or underwater depth of ocean floors, which is given through oceanic mapping in a chart datum. As the water level is not constant over the time, we introduce also a mean sea level, the average water level. But we know that the water level vary with the tides, so we have to monitor the water level permanently. As there are different reference surfaces that are independent from each other, we have to be very cautious against which of the reference surface the dynamic water level changes are monitored. Now, we set a cargo ship in the water. And in dependency on the type of the ship and the load the ship carry, we have to consider a different draft. The underkeel clearance, which is important to know for safe shipping, is then a result of all the variable parameters given by the sea level and the ship's draft. Now we turn our attention to the right side of the picture, where we have a GNSS core station and a tide gauge. These are referenced stations because geodesists estimated very well the height about the ellipsoid and the geoid. The tide gauge provides us with the height of the water level in respect to the reference surface, and with this the actual depth of the water column. And considering that also the ship is equipped with a GNSS receiver, we can use the reference station to relate also the ship's bottom to the depth of the sea. From this information, it is not difficult to calculate the underkeel clearance for safe shipping. The same principle applies also for passing of the ship under the bridges. The different lines and arrows in the picture now clearly display the otherwise invisible geodetic contribution to daily ship transport across the world. Now we turn to another example. The sea level change is a quite familiar and important parameter that reflects the climate change. In the figure on the left, the graph shows the development of the sea level rise over more than a century. In the last decades, with the rate of around 3 millimeters per year. But the basic question is, how can you measure on a global scale a rate of just some millimeters per year? In former times, such measurements relied solely on globally distributed tide gauges that have not been linked to each other. Such result can be easily questioned. Since the last decades, the satellite altimetry system supplement the measurement, in the graph indicated in red. In the right figure, you see the orbital tracks of satellite altimeters observing sea surface height. They built a mesh covering all ocean, just with the exception of the polar regions. In any case, a reliable result depends on a precise global vertical datum delivered by geodesy. And now we look how complex the measurement of the sea level change with altimetry system works. Usually, the people take it for granted that there are some satellites like altimeters that are doing some measurements and deliver resulting values we are familiar with. The reality is far away from that. In the figure, you see an altimeter satellite measuring the distance from satellite to the sea level. But what tells us this value without any relation to a reference frame or datum? Without additional relations, the observed range has no relevance. And not just the satellite, also the sea level needs a relation to a reference frame. Throughout this webinar, we already learned the different reference surfaces and the relation between them. We have to apply them also in this example because without a stable reference, we cannot quantify the sea level and its changes. But still, as we don't know the exact height of the satellite, the measured range between the satellite and the sea level is of no use. What we need to know is the precise satellite orbit height in respect to the ellipsoid and geoid, which is the same reference as for the sea level. In this way, we link or relate the satellite height to the sea level and can exploit the altimeter distance measurement for sea level estimation. The satellite orbits has to be measured very precisely, as any error of the satellite height propagate immediately into the result, the sea level height. But how to measure satellite height? For this, we need referenced ground station, means station with exact relation to the reference frame that observe continuously the flying satellite. The geodesy use different techniques for observing satellite positions and orbits. One can measure the distance between the satellite and the ground station with help of laser beam, the satellite laser ranging, as well as by receiving signals by satellite broadcasted from known ground station, like in case of Doris system. We use also GNSS, as the satellites are usually equipped with the GNSS receiver. But don't forget that by using GNSS, also here, like by all other satellite missions, we have at first to know their own position, means their own orbits. Then even the navigation satellites don't know their own position without continuous observation from referenced station network and calculations carried out by geodesists. And now eventually we can use the observed range between the altimeter satellite and the sea level to calculate the sea level height, as we have all we need for that. We have a stable global reference frame that we need for the quantification of the sea level. We have also reference station network on the ground that we can use for monitoring the altimeter satellite, as well as a satellite navigation system that we can apply. The collected observations are then analyzed by geodesists to calculate the precise satellite orbits, which means the height of the altimeter system. And finally, subtracting from the altimeter height the observed range, we obtain the sea level height. At the end, we complement this system with tide gauges for observing the sea level along the coasts. Also, the tide gauges need to be related to the reference frame or a vertical datum to obtain referenced value. Why is it important? We show you in the following slide. But first, we look at another phenomenon. During the ice ages, the huge mass of ice accumulated over Scandinavia pressed the Earth crust down. After the ice melted, the elastic crust started to move back to its original position. This is what we call the postglacial land uplift. With the red coloring in the figure on the left is indicated the area of such land uplift over Scandinavia. In the graph on the right, you see then the uplift rate for the particular GNSS station in Kiruna, which has the average uplift rate of 7 millimeters per year. Such land uplift with the rate of around 1 centimeter per year over the large area could not be seen without a precise vertical datum. Now we couple the two different processes, the postglacial uplift and the sea level rise. Imagine You would monitor sea level change at one particular point on the coast, like indicated in the picture on the left. The red dot originally at the sea level is after some decades significantly above the sea level, and one would logically conclude that the sea level is sinking. But is it really so? Your observation resumed just from the relative difference between the coast and sea level in this particular area. Have you accounted also for the dynamic of the Earth crust? Look at the explanation in the figure on the right. Assuming postglacial uplift at the coast with the rate of 10 millimeters per year and considering the sea level rise with the rate just of 3 millimeters per year, one would, without a stable reference frame, make probably a wrong conclusion. This example should demonstrate how important it is to account for all the different dynamic processes that happened simultaneously. With these practical examples, we come to the end and summarize today's lessons related to the height systems. Count its vertical datum should be based the physical shape of the Earth. The height component is not simply geometric value. The Earth can be represented by two different surfaces. The ellipsoid, which represent the geometric approximation of the Earth's shape, and it is reference surface for GNSS height that cannot account for the gravity. And geoid, representing the physical shape of the Earth, is the gravitational equipotential surface at the sea level and reflects the way the water flows. It defines the physical zero high level. Distances between equipotential surfaces don't correspond with the geometric distances. And physical height is a metric specification of a physical quantity. Thank you for your interest throughout the webinar series related to the geodetic datums. We are happy to answer further questions and support you.